Hello, everyone. Welcome to Chapter 8, Comparative Planetology, the Origin of our Solar System. In this chapter, the main things that we learn are key characteristics of the solar system that must be explained by any theory of its origins, how the abundances of chemical elements in solar system and beyond explain the sizes of planets, how we can determine the age of solar system by measuring abundances of radioactive elements. This is radioactive dating. Why scientists think the sun and planets all formed from a cloud called solar nebula. How the solar nebula model explains the formation of terrestrial planets. What are the two competing models of how the Jovian planets evolved, and how astronomers test the solar nebula model by observing planets around other stars. So the three key properties of a solar system, which should be explained by any theory of its origin. Obviously, no one was present when the solar system formed, so we have to make a theory of how it must have happened. And these three very important properties of our solar system, they should be consistent with our theory of how the solar system was formed. The three properties are sizes and compositions of terrestrial versus Jovian planets. The four inner planets, Mercury, Venus, Earth, Mars, are small, rocky, and dense, whereas the outer four planets are all called Jovian planets, also called gas giants. They are big, composed primarily of hydrogen and helium, are relatively large and less dense. Directions and orientations of planetary orbits. All planets orbit the sun in the same direction, and all their orbits are nearly in the same plane. Sizes of terrestrial planet orbits versus Jovian planet orbits. So all the terrestrial planets are very close to the sun, while the Jovian planets orbit far from the sun. So all these facts must be consistent with the theory of origin. Composition of the solar system. Hydrogen is the basic building structure of the whole universe and even the solar system. So 71% of the hydrogen of the solar system is hydrogen, then helium, and then 2% other elements. All the big things in the solar system, like the sun, the gas giants, they are made up of hydrogen. And other elements are primarily in the tiny terrestrial planets. In the sky, in various places, we find nebulae of gas and dust. Those are the death remnants of old stars and also the birthplaces of young stars. Stars go through many cycles in which old stars die, and the debris from them forms new stars, young stars. And in that process, elements are recycled and heavier elements are formed. And heavy elements like iron, nickel, uranium, gold, silver, all of these are made by repeated processes of the death and birth of stars. So in the beginning of the universe, hydrogen was formed, and then by several cycles of the star, when we get to the chapters on stars, we'll talk about this. By the life cycle of the stars, hydrogen converts into heavier and heavier elements. And therefore, their abundances are less and less. Still, the first 30 elements in the periodic table are by far the most abundant compared to the rest of them. So here is a table showing the abundance of the various elements of the periodic table. And you can see hydrogen is the topmost, helium is the second topmost, and then surprisingly, lithium, beryllium, and boron are not as abundant, but then carbon, nitrogen, oxygen, these are still low atomic mass elements. These are quite abundant in the solar system. The one thing to notice is that this scale is a logarithmic scale. So each next step on the vertical axis is 10 times greater than before. So if you look at the helium and hydrogen, then hydrogen is not just 1 point more than helium, but it is 10 times more than helium. So small differences in here mean a lot. We can find the early composition of the solar system by catching the meteorites. The stuff that is on Earth gets recycled because of erosion and weathering and many other processes, but the meteorites that were formed towards the origin of the solar system, they've been preserved pretty well. So when we catch those meteorites, we can, those are one of the oldest types of things that we can see. We can also use the meteorites to find the age of the solar system by radioactive dating. Some of these elements which have radioactive isotopes and they decay, they change from one element to another by decay. And those are like nature's clocks. For example, rubidium changes to strontium, uranium changes to lead, potassium to argon, carbon to nitrogen. And they all have these different half-life. This half-life is a measure of how fast they change. Carbon 14 converting to nitrogen, its half-life is 5,730 years, which is quite short. So this is more suitable for the carbon dating that you must have heard about. This is used for archaeological purposes on the Earth. But when it comes to archaeology of the solar system, these other elements like rubidium, uranium, and those are helpful. And they can help us find the age of things as old as 10 million to 4.56 billion years old. And from that, we have found that the solar system was formed 4.56 billion years ago. So how was the solar system formed? So it is thought that it started with a diffuse, roughly spherical, slowly rotating nebula made up of gas and dust, which was contracting and at the same time rotating. And because of conservation of angular momentum, its speed of rotation kept on increasing. And as the speed of rotation increased, the centrifugal force caused it to stretch along the radius, making it into a take a disk form. And it started, as it contracted, it started spinning faster and faster. This is because of conservation of angular momentum. This kind of thing is seen when you watch figure skaters. They start out spinning not that fast, but their arms and legs are spread out away from their axis of rotation, so they have a larger moment of inertia, but as they pull their arms and legs in, their moment of inertia reduces and they start spinning very fast. In the same way, when the disk contracts, it starts to spin faster and faster. In fact, most of the objects in the universe are spinning, and they're spinning because of this reason. And they're spinning quite fast because of this reason. So how do we learn about the formation of solar system? We look at different places in the universe and we see different protoplanetary nebulas, protoplanetary disks, which are which are their own solar systems, planetary systems in the process of formation, and we see that they are quite similar to our solar system. Temperature distribution in the nebula. As the nebula was starting to rotate faster and also contract at the same time, there was the central portion of it contracted so much that it produced heat because of the contraction, and started a nuclear reaction and formed the protosun, which produced the heat. And so in the center of the solar nebula, the sun was formed. There was a source of heat, and that produced a temperature gradient where it was hotter closer to the sun, closer to the center of the disk, and it was colder further away. And this caused some differences in what kinds of planets formed closer and what kinds of planets formed far away. So closer to the sun, the small and dense terrestrial planets formed, and further away, the gas giants formed. And this is because closer to the sun, because of hot temperature, the gases could not condense. But further away, where the temperature was less, the gases could condense. The water could condense to form ice, and other gases could condense around nucleation to form these gas giants. So as the disk kept on rotating, the disk broke into rings. The disk broke into several rings, and then there were collisions and accumulation. There were these small planetesimals, about 1 kilometer in size. Planetesimals are the initial small nucleus around which more and more matter aggregated to form the full-fledged planets that we have. They just kept colliding into other pieces to form bigger and bigger pieces, which eventually form the planets. This is how the terrestrial planets were formed. The terrestrial planets were built up by collisions and by the accretion of planetesimals by gravitational attraction. However, the Jovian planets formed by gas accretion. So Jovian planets formed by collecting the gas in the slightly colder environment further away from the sun. We keep testing our theory of the origin of the universe by observing exoplanets, planets that go around other stars. And by observing their formation and their properties, we learn about how our planets formed. What are some ways of watching, of observing and learning about the properties of exoplanets? So one is the astrometric method and the other is the radial velocity method. So the main thing is that when a planet goes around a star, it causes the star to wobble. Even though this wobble is very small, with very precise instruments, we can see the wobble. If with a very precise telescope, we can see the star wobble side to side. If we are able to measure that, then we know that there is a planet orbiting that star, and we can learn about the properties of that planet around that star. Those planets are called exoplanets. Or the other one is the radial velocity method. Again, if the star is wobbling, its velocity is, sometimes it's moving towards us, sometimes it's moving away from us, and we can figure that out by measuring the Doppler shift in its light. We can tell a lot by measuring this Doppler shift. We can tell the period of the orbit of the planet and other things, which we'll talk about later. Getting back to the formation of our own solar system, let's talk in more detail about how the different processes happened. So here is a vast rotating cloud of gas and dust. Kelvin-Helmholtz contraction causes the rise of heat, increased density, temperature. The protosun forms and begins to grow. Tens of millions of years, protoplanetary disk forms, rocks and ice particles collide and start to form planetesimals. In the inner disk, rock particles collide and grow. In the outer disk, ice particles collide and they attract gas. This is the difference between how terrestrial planets formed and how Jovian planets formed. This keeps happening for several 100 million years. The terrestrial planets are in molten state. Accretion of terrestrial planets, protosun becomes hot enough for nuclear fusion to begin. So before it is just hot because of the compression and the heat, and now the nuclear reaction starts, nuclear fusion starts. Jovian planets accrete from gas in outer disks. Terrestrial planets heat up, begin chemical differentiation. Chemical differentiation is where the hot iron and nickel sinks to the center, forming the iron crust, and the light particles which make the soil and the rocks, they rise and form the crust and the mantle of the earth. And then there is a next step where a very powerful, like solar wind, it is like solar wind, but slightly different. A T-Tauri wind sweeps away gas and dust, leaving planets, moons, asteroids, Kuiper belt, and Oort cloud, making the solar system much cleaner. So this is our theory of how our solar system formed. Now let's get back to talking about exoplanets or extrasolar planets. With the development of many new kinds of telescopes, we have found thousands and thousands of exoplanets, and this graph shows records of these exoplanets. Here, On the left-hand side, it is showing the star around which the exoplanet has been found. And on the right, there's mark of one or more exoplanets which have been found. If we read closely, it also labels the distance of the planet from the star and its mass. And you can compare how it looks like compared to our own solar system. The top line is for our own solar system. All right, once we know that a certain star has a planet around it, an exoplanet around it, that exoplanet may be so small that we still may not be able to see the exoplanet. We may only be able to see its effect on how the star looks like. But with that, even with that, with clever and scientific knowledge, we can learn a lot about the properties of the planet. And these are some ways in which we can do that. For example, if we look very carefully at the star, and if the planet orbits the star in such a way that it moves in front of it transits the star sometimes, then by how much the brightness of the star gets reduced, by looking at that, we can estimate the planet's diameter. And then when it transits the planet, we can also look at the absorption lines that are produced. And if absorption lines are produced, those are evidence of the planet having an atmosphere. And we can also tell what kind of gases are present in the planet's atmosphere. On top of that, when the planet moves behind the star, the infrared glow from the planet's surface is blocked from our view. The amount of infrared dimming tells us the planet's surface temperature. So we can tell the planet's diameter, its atmosphere, its temperature, its period around the star. What are some ways in which we can detect an exoplanet? Some other methods. One of them was obviously by the wobble and by using the astrometric method and the Doppler method. Another method is by microlensing. So obviously there's gravitational lensing. Sometimes when a star passes in our line of sight, when we are looking at a distant star, then it distorts the image of the star, makes it brighter. But after the first fluctuation of brightness, if there's another minor change, that means there's another small body that passed in our line of sight, and that is a planet around that star. That is microlensing. So those are some of our methods of learning about exoplanets, and from the exoplanets, understanding the origin of our own solar system. With that, we get to the end of this chapter. There are some slides here summarizing the information of this chapter in a very concise way. Please do read them. And with that, we finish the chapter. Thank you.